Okay, this is a work solution to the Dijkstra, which is this first question, and the Prim or DJP algorithm questions. So I'm going to work through them and try and discuss answers as we go through. So we need to start off with the copy of the graph. All the information from this graph in figure 1 is actually in the working version we've got below. So this represents a network of roads. The number on each arc is the length in kilometres. Use Dijkstra's algorithm to find the distance from S to G, stating the shortest route. State both the shortest distance and the shortest route from S to H. So let's go first of all for the first one. We start at S, and according to Edexcel, you label these numbers in here. It doesn't matter if you start 1 or 0 really, but I'm going to start with 1, and it cost me nothing to get there because there's no working. Now I'm going to update the connected nodes. So this would cost 10 from S, and this one would cost 13 from S, and this one would cost 17 from S. So now what I do is I work through and find the next cheapest one. Well, that's B, so this is item number 2. It costs 10, and I update anything from there. So 10 plus 4 is 14, and that came from B. What's my next cheapest node? Next cheapest node is A, so I go back to A. Number 3, currently costing 13, and we connect to anything else that we can update. So 13 plus 2 is 15, which is better than the value already there from the start. So it's better to get to C by coming from A, and 19 to E, and that came from section A. Look at the next best starting point. Well, strangely enough, D is better than the 15 from C, so this is position number 4. It's 14 from there, and we update everybody it connects to, including coming backwards to C. So 14 plus 2 is 16. I really wouldn't need to do it. 16 from D. That doesn't make that better. Moving forward, I've got 19 into F, which is from D. And here I've got 28 to G. Now, the fact I've got to G doesn't mean I've finished. I've got to see, is there a better way? So I'm going to see whether or not F updates it at any point. Next cheapest node to go to. We just did the 14 there, 14 plus that is that. So we're now coming back to the 15. So we're doing position 5 for 15. No point updating this one because we've already processed that node. 15 plus 1 is 16. So I can get there for 16 via C. And I can get to 18 via C from here. Next cheapest node is F. F is number 6, costing 16. 16 goes 23 to the top. 3 for F. Now, and I'll just update the other bits coming back round. F goes to E for 17. And H is 21 coming from F. Look at our cheapest nodes. Now, I can actually say, because there are no new nodes to come into here, and this was my target, and my target has been reached, I don't actually need to process the further nodes. So the target reached, and no other paths. Can be found. So I could actually say this is never going to get better than 23. I haven't properly processed that node. What I would do, and we'll go through and show that this doesn't get updated now. So my next cheapest one out of these is to come down here, back down to 17. 17 gives me position 7, 17. It's not going to update this one, it's not going to get any better, but it is going to improve the H. So that is 20 from position, so that was F, not E, from E. Process the next node. Well, this now is the cheapest node, so that would be number 8, and it costs 20 to get there. And finally, I can update the 23. But in the first pass, I didn't actually need to do all of these, because once I'd got both of them, and there was no other way to come in, those two nodes, that's been processed, I can complete. So, use Dijkstra's to state the shortest route from S to G. Well, the cost is 23, and because we've been noting as we went through, we can run the whole thing backwards. We go 23. If it wasn't, you'd have to do Edexcel's thing of checking what's the next one on the critical path coming back, and that would be where if I subtract the path and I get this number here, the current weight, so 23 minus 7 is 16, that's on the critical path. 23 minus 14 is 9, so that wouldn't be. 16 minus 5 doesn't give me 11, so I wouldn't go backwards. 16 minus 1 doesn't give me 17, so I wouldn't use that one. So 16 minus 1 gives me 15, correct. So I am coming back to C, which is what we noted here. Keep running round. 15 minus 2, no, that's not on the critical path. 15 minus 3 to give me 17, no, it's not on the critical path. Then 15 minus 2 gives me 13, could be on a critical path. 15 minus 17 is less than 0, so not on my critical path. So now we've gone back to C. C actually tells me go to A anyway, so come to A. 13 from the start is on the critical path. The other one, 6. 13 minus 6 doesn't give me 17, it gives me 7. So not on the critical path. So my critical path is easiest because we've been tracking it. We end at G. We came from F. From F we came from C. From C we came from A. And from A came from the start. So that was for SG. I can do the same thing for SH. Now SH has been processed. I can actually go back and say SH as well. So SH costs 20 and do the same thing. I can run it backwards. H goes to E. E goes to F. F then goes to C. C goes to A. And A go back to S. And we go 13 backwards. Okay, they're my two solutions to those two questions. The next one, using Prim's algorithm, start at A and find the minimum spanning tree for the network. You must list all the arcs you form in your tree in the order you select them. So starting at A, Prim's algorithm says add the next cheapest arc to your network, your existing network. Well, my existing network is only A, so I can do A to B for 22. I've now got A and B. Next cheapest arc to add is BC, which is 24. Next cheapest node to add is C to F for 18. CF, which is 18. Look back in my graph, connecting up. Next cheapest one is actually this 20 back here. So CE for 20. CE and 20. Next cheapest one that doesn't form a cycle. So I've got a 28, a 30, a 27, a 25, and a 25. This 25 creates a cycle, so we're not going to use it. Okay, it's not adding a new node to my prim's algorithm. Prim always likes to add a new node. So the 25 there, AD gives me 25. And 25. Next cheapest one to add is going to be the 26, which is DG. I've messed up in those last two. CE 20 correct, but AD is not my cheapest. Just remove those. Yeah, I made my mistake here. Tried adding 20. Then after that, the next cheapest one is 23 over here, which connects to G. So FG 23. After 23, then I do AD 25. AD for 25. Then we're looking for 25. After the 25, right, the 26 creates a cycle. It's not a new node for us to G. The D at 27 creates a new, doesn't create a new node, so it's not in my cycle, so I don't want the 27. Next one then is this 28, which is EH. Next one after that, 29, no good, because it's connecting to connection. 30, reconnecting again, so we're not going to use that one. Next cheapest one is number 31, which connects to I. So it's HI for 31. If I actually check the number of nodes I've actually got eight arcs, and there are 2, 4, 6, 8, 9. So yeah, we have exhausted the spanning tree. This must be a spanning tree. Arcs minus 1 plus 1 equals nodes or vertices. Edges plus 1 equals the number of vertices. I can stop. Calculate the cost of connecting these alarm systems. That will give me 22, 40, 66, 64, 43, 68, and 59. So 132, 180, 191. I'll make the total to be on that minimum spanning tree. Right. Okay, I've got another copy of the map so we can work on it. It's discovered some of the alarm systems are already connected. There are connections along B, C, and EF. Since they already exist, it is decided that these arcs are part of the spanning tree, so we don't need to put any other new ones in between those nodes. So using Kruskal's algorithm, find the minimum spanning tree, including B, C, and EF. So Kruskal's algorithm, we start with our same values, our graph. First of all, we already know the 24 and the 30 have been done. Spanning tree. Don't need to state the new minimum cost of connecting the 9 buildings. Right, we're going to assume these two have already been done. So we're not going to do the total for the minimum spanning tree. We'll do that as a separate question as we go through. So Kruskal, he wants the cheapest nodes in any connection we've got. So to start with, cheapest one is CF for 18. Then next one to look at is what's our cheapest node after 18. 18 will give me number 20, which is CE. Now the problem is we've already connected CF, so this would not actually not connect two unconnected graphs or connect a new node, so this one doesn't work. So we ignore CE20. It's not going to be done this time. And moving on, anywhere on the grid is fine. So my next cheapest one is 22 over here. So AB for 22. Next cheapest after 22 is CG for 23. It wouldn't have to actually be part of the graph to add on to it. Next one to add is a 25. Don't think we've got anything better than a 25 I haven't considered yet. No. And we've got a choice of 2. But we're not going to use that one because it will create a cycle A, C, B. So let's just say we're not doing A, C, 25. That would lead to ACB being closed. CE up here would have led to CEF being closed. And we don't want any closed loops. Keep looking through. Next one, next cheapest I can see is 25, which is at AD. And connect it in. Then I look at the 26. 26, not connecting anything new, and it's not connecting to broken networks, so we're not going to do the 26. DG for 26, no. And same reason, we're not going to do DF 27. Next cheapest one is 28, which is REH. Well, we didn't do the 20 up there either. Actually, just before this, we shouldn't have done BE either. So BE, so I don't know what I'm drawing it in for. So BE for 27 also didn't work. Then we get EH for 28. HF 29, not needed. So I'm not going to use that one. Next cheapest one is HI for 31. So my graph is now connected. I don't need to actually connect any more points on. So that's the end of the graph. So the minimum spanning tree is actually the 24 and the 30 plus this new total. So we've got 18, 40, 63, 88, 108, 116, 117, 147. So that's the actual cost, as asked for in the previous bit of the question. And the minimum spanning tree is that plus the 2 extra nodes, which is another 54, which gives us 201. Check, we've done the others. So that's the minimum connection, that's D, is that bit, the actual cost. That was C part 1. The question is, why is this better than Prim's for this? And the reason it's better than Prim's. Prim's algorithm, you've got to have a starting point, and it doesn't give us this immediate start weight. I think it would still work. Part 2, Prim's, because it's supposed to start with a growing network, you're not supposed to have disconnected parts from the graph. But I would still say you can solve the problem using Prim's. But the reason they're looking is basically because C and E, sorry, BC and EF are disconnected. It wouldn't be a full Prim's algorithm. But my reasoning on it is it doesn't matter which node I start at. If I clear out all these extras, or actually I can self-copy again for us to discuss. I'm pretty certain I could apply prim to create a connected graph, just following the rule of saying once I connect somewhere, I'm effectively saying B and C are now the same. I'm saying E and F are the same. This is an important idea when it comes to critical path analysis. So if I did a prim from A, I'll connect A to B, and I'll be adding 22, which would automatically also add BC for 0. Okay. Look at my next cheapest node. Well, CE is my CF is 18. So CF is 18, and that now gives me E as well, FE for 0, because they've already been connected. Looking through now, what's my next one I can connect? 18, I could do the 25, oh no, 23 FG. So what I've actually grown so far was AB, and gave myself BC because of it. Because of that, I could now connect CF, which gave me E because of it, and now I'm connecting my 23 for FG. Connecting up again, AD is 25. I think that's the cheapest AD. I wouldn't do AC because it's a closed loop. So we go AD for 25. Next cheapest one, can't do the 26 or the 27 from there because both of those would connect to G and it will give us closed loops. So that's not needed, not needed, not needed. So DG and DF, both of them would lead to closed paths, not going to give me a connection. So my next one is EH for 28. Oh, sorry, 27. Wouldn't do the CE for 20 back here. Not going to get it. The important one is which nodes are you actually connecting on Y. 25, so I'm now connecting EH. 28. Then FH, not needed, not needed, not needed. Next cheapest one to connect now is HI for 31. And what's the total cost for this? 40, 63, 63, 88, 108, 116, 147. Which hopefully is the same as what I made on the other one, the actual cost. It still works. I don't see why they're saying it shouldn't. It's just that it's actually breaking the rule because of these being connected. So that's the end of that question.